In this video, we're going to study differential equations and with that, talk about applications of integrals. So we've already seen differential equations in some capacity when we were studying back in Module 4A and 4B, acceleration, velocity, and speed. Those were all differential equations whose solutions we determine. But we have these three objectives that we're going to hopefully get through by the end of this module. Okay, so a differential equation, essentially think of it as just a rate equation. So there's a couple different forms here. The one that we're really going to key in is this y prime is equal to f of x and y. So the derivative of y, the rate of change of y, is a function of two variables. These other notations we will see, perhaps this one we'll see for sure, and then this is really just Leibniz's form of this. So instead of using prime notation, we use Leibniz notation. Same thing. This one is a little bit more complex. It's not as clear what it means, but they all mean the same thing. And really what we're going to do here is focus on only the first derivative. So for example, we do have different orders of differential equations, and so the order the order of a differential equation indicates the highest appearing derivative. So for example, first order means that you have only first derivative appearing, being the highest derivative. Second order, the highest appearing derivative is second derivative. Third derivative, or third order, would be third derivative, etc. Okay, so just to go through and walk through some examples of differential equations, you could have something just like y prime is equal to k. That's a differential equation. Y prime is equal to y. This one we'll actually see in the next video. This one is going to be an exponential growth model. And you could have y prime minus y plus x squared equals 2. That's still a differential equation. Okay. Some function or some equations that are not differential equations would be something just like y is equal to kx. So a basic line. You could have y is equal to 2. Okay, so notice there's no derivatives appearing. You could have xy plus x squared minus 2 is equal to 0. That's not a differential equation. It's not involving a derivative. Okay, the result that we get from a differential equation we call a solution. So after we go through and find the antiderivative, we call that antiderivative a solution to the differential equation. So in essence, what this is saying is that if we were to take x, our solution, which we call f of x, and its derivative, substituted into our original differential equation, we should get 0 if we move everything to one side, or the result is equality. Okay, so if you get equal sides, it'll be a solution. So here, what we want to do is we want to test if the function y is equal to x to the minus 3 halves is a solution to the differential equation given here. Well, I need to substitute in for y double prime, y prime, and y. Okay, so I need to first find these derivatives. I have y, but y prime, this is just, we're going to use the power rule. So bring the power down, minus 3 halves, x to the minus, and now I decrease the power by 1, so my power becomes minus 5 halves. Y double prime, I'm going to get a 15 over 4 after the multiplication, x to the minus 7 halves. Okay, so I can go ahead and go through this arithmetic. So I have 4x squared, and then I multiply by 15 over 4, x to the minus 7 halves, and then add 12, and then my 12x times my first derivative, which is minus 3 halves, x to the minus 5 halves, plus 3 times, and then just my my solution here. Okay, so going through this arithmetic, I get 15x, and now if I add these, this is 4 halves, this is going to be minus 3 halves. And then going through this arithmetic, I get a what? I get a 6, and then a minus 18, x to the minus 3 halves. And then I add to that 3x to the minus 3 halves. Okay, so now I have all the same power functions appearing. So I just have to add the coefficients, and I end up with 18, a positive 18, and then a minus 18, so I end up with 0. So this does work, and y of x equals x to the minus 3 halves is a solution. Because after, again, according to this definition, I want to either get one side equal to 0, or I could have said, is this equal to 0 from the get-go, and set it equal to 0, in which case I would drop all these, and then I'd get 0 is equal to 0, and that would be true. So you can either work one side to the other, or you can try and work both sides simultaneously until you get equality again. Okay? And remember, at the end of the problem, you should always state your conclusion in a sentence. So in this one, you just have to say it is a solution. Okay, so we can verify solutions, but we want to talk about what types of solutions exist. So the solution that we found back here, we don't really know what this is. I would probably call this a particular solution, which we'll see in a minute. But there's two types of solution. There's a general solution, so a solution where you have an undetermined real constant in there. So constant c that we get from integration. Okay, and we'll see how to solve this. And well, we've already seen antiderivatives. So if you get an antiderivative where you just have a real constant in there, that's going to be a general solution. Now, the other type is going to be called a particular solution. But before we get there, we need to introduce one bit of terminology. A boundary value is a condition accompanying a differential equation. So it'll often appear as y is equal to, and then or y of some value, which is your x value, is equal to a y value. Okay. So we call it a boundary value, but and if that boundary value has an x value or an independent variable value that is 0, then we call that an initial value. Okay, so just a little change in terminology there. Okay, and so as I mentioned, the other type of solution is a particular solution, and in that one, these constants c are actually determined. So we should not have any constants appearing in our solution, and so just a couple examples. So for example, in the first one, you could have the constant being minus pi, and the second one, it could just be 1. Okay, in either way, the particular solution should not contain any undetermined constants. Okay, basic introduction to differential equations. In the next video, we will discuss one technique that we will focus on in this module to determine these solutions to differential equations.